Okay, in this video, we're going to look at graphs of sine and cosine. And the next class period, we'll talk about graphs of other functions, and then we'll look at inverse trig functions. But today is going to be about sine and cosine. Now, I have the graphs already over here, but let's take a look at where they come from. And to do that, I'm going to go to this website here. So if later on you want to go back and take a look at this, this animation, you can just type this into the address bar, and that'll take you there. But I have it already here. So let's take a look at what's going on in this picture. Now the circle on the right-hand side is representing the unit circle. And we've taken a look at the unit circle before. And we know on the unit circle, the y-coordinate will correspond to the value for sine. And as you can see, this is labeled a sine wave made by a circle. So how is this doing it? Well, I'm going to go ahead and start this animation right here. So you can see right there, if I'm at the right-hand side of the unit circle, my y-coordinate is 0. And you can see how it corresponds to the y-coordinate of 0 right there in the orange graph. Now, as I move up on the circle, my y-coordinate is increasing, and you can see that the orange graph is to the left is increasing. And then I go down to the bottom of the unit circle, and that orange graph is at the bottom, but then I go up, and it just kind of keeps repeating. As I'm going up and down the unit circle, my y-coordinate is increasing or decreasing, and that means the graph of sine is increasing or decreasing. And I can just keep going around this unit circle making that sine graph, and that's where it comes from. And that's why these sine graphs go up and down like that. We make a sine wave. So let's go back here to the notes then. Now if I go ahead and just make a table of values. Now remember, the sine, the value of sine correspond to the y-coordinates on the unit circle. So at 0 radians, the y-coordinate is 0. That's where that came from. At pi over 2 radians, the y-coordinate is 1. There's that. At pi radians, the y-coordinate is 0. At 3 pi over 2 radians, the y-coordinate is -1. And then back at 2 pi radians, the y-coordinate is back at 0. So that's, and then it just repeats itself. And that's these points right here, 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, and 2 pi 0. And then the graph just repeats and so on. And we can do the same pattern on the left-hand side. And that's where a sine graph comes from. And if we look at cosine, you're going to see it's very similar. Now remember, on the unit circle, cosine corresponds to the x-coordinates. And so I just went ahead and labeled all the x-coordinates for these various radians. And then I plotted those points. So at 0 radians, the x-coordinate's 1. At pi over 2 radians, the x-coordinate's 0, and so on. Plotted the point 0, 1, pi over 2, 0, and so on. And that gives us one cycle of the graph, but then it repeats over and over again. And the sine graph and the cosine graph look almost exactly the same. It's just one is shifted. If I shift the cosine to the right, pi over 2 units, I get the sine graph. Or if I shift the sine graph pi over 2 units to the left, I get the cosine graph. So anything that can be described as a sine can also be described with a cosine. So yeah, there we go. Now, before there's any kind of transformations, we're going to talk about those in a second. One way to remember which one is which is if you draw one cycle or one period of the graph, so one time before it starts to repeat itself, starting at the origin, the sine graph makes an S. That's kind of a backwards S, but it makes an S. The cosine will make a cup. And that's one way to remember which one is which. So let's talk about transformations of these now. Now, if we look at them individually, we get these things. And I can barely fit it all in one screen. Because these things have so many direct applications in science, I mean, everything we do in math has applications, but you guys have heard of sine waves, cosine waves, sound waves, light waves, even the tides can be modeled with these graphs. They come in and out, in and out. There's other terms that are often used instead of terms that we're familiar with in math. So like we have vertical stretches, but when we're talking sine and cosine waves, the vertical stretches actually affect what we call the amplitude of the graph. Now here's a definition for the amplitude. So the amplitude is half the distance between the max and the min values. But a way to think about it geometrically, so here's a graph, it's going up and down, up and down, up and down, and so on. If we look at the middle, the midline of it, how far up does it go from the middle, or how far down does it go from the middle? That represents the amplitude of the graph. That's what it means geometrically. So measuring from the middle to a maximum value or to a minimum value. And that's going to have to do with our vertical stretch, A. The horizontal stretch will affect the period. How long does it take for the graph to complete one period of the graph? Going up here, we can see it takes 2 pi units to complete one period of the graph on both the sine and the cosine. But if we stretch this thing out vertically or compress it, horizontally, if we stretch it horizontally or compress it horizontally, then that's going to change the period. And that's going to be based on what we multiply x by. The period is always going to be 2 pi over b, whatever that is. And then we can have horizontal shifts, just like normal. And horizontal shifts in the case of these graphs we call it the phase shift. But it's still just a horizontal shift. Have we shifted it left or right? And that's going to be if you add or subtract something from x. That's our phase shift. So that's just some vocabulary. But let's put all this together, because this is looking at each one individually. But what if you have a change in amplitude, a change in period, and a change in the phase shift? And you put it all together, and we even put it together with a vertical shift. So what happens when we put all these things together? Well, then we have this. And we can write the equations as either this if it's a sine, or this way if it's cosine. Now the only thing that we have to be careful of is our phase shift. Because if we have a coefficient of x that's other than 1, our phase shift isn't just the value of c. This is the only special thing. Because remember, and again, if you think back to when we did horizontal shifts before, it's based on what you're adding or subtracting just to x. And if I'm writing it this way in purple, this c is being added or subtracted to bx. So anytime you have a coefficient of x other than 1, you've always got to factor that coefficient out to see the phase shift. And then your phase shift is actually going to be c over b. So putting it all together, this is what we get. The amplitude is the absolute value of a. The period is 2 pi over b. Your phase shift is c over b, like I said, because we have to factor out that b. And then, of course, your vertical shift will be based on d. Once you know these things, you can come up with a graph for a sine or a cosine graph. And I'll show you, it's actually really not that bad to graph these. So now we're going to just take a look at 5 examples for you. Okay, so let's take a look at this one. Now I've already done this one, but let's take a look. So if I wanted you to graph this, it's easiest if you identify A, B, C, and D first, and then you can identify these things from that. So be careful. To identify A, B, C, and D, you want to think of it written this way. And so remember the D is actually a -2. They just put it in the front instead of at the end. And let me talk real quick about why they did that. If they put it at the end, it would look like this. And then it becomes a little confusing. Wait a minute. Is the 4x minus 2, is that like your bx minus c? So does the 2 have to do with c? Or is the 2 have to do with d? Which way does this go? And I will tell you that it could be written this way. If it was written this way, it's implied that the -2 is d. Because here's the rule. if you have multiple terms, remember terms are separated by plus or minus signs. If you have multiple terms and there's no parentheses, then only the first term is the argument for cosine. And it's the same for all the trig functions. So if it's written this way, it is implied that only the 4x is part of cosine. If you really wanted the 4x minus 2 to all be part of cosine, you would have to write it like this. You would have to go and write the 4x minus 2 in parentheses to show that the entire quantity is the argument for cosine. So sometimes people don't put the d in front like this. Sometimes I'll write it like this, and you just have to know the rule that the minus 2 is not part of the argument. Or sometimes people will just put it in front to make it clear that it's not part of the argument. Okay, so now that we got that, now it's easy to see that a is 1, b is 4, there is no c, so c is 0, and d is negative 2. And then we can easily find this stuff. The amplitude is the absolute value of a, so it's 1. The period is 2 pi over b, which in this case is 2 pi over 4, or it simplifies to pi over 2. There is no phase shift because c was 0. And we're going to have a vertical shift down 2 units because d is negative 2. And from this, we can do our graph. Now, here's what I recommend with the graph. There's different strategies to doing it, but here's the way I like to do it personally. First of all, when I set up my axes, I usually count by ones unless I have some crazy amplitude. Like if a was 100, obviously I wouldn't be counting by ones then. But usually we can count by ones. But as far as on the x-axis, I use my period to help me with that. My period is pi over 2. If I go back actually to this graph in the beginning, remember that one period, the cup for cosine? Look how many spaces it takes to complete one period. 1, 2, 3, 4 spaces. So if I choose my scale so that it will always complete one period in 4 spaces, that means 4 spaces have to be equal to the period. It'll make it much easier to graph. And so you're going to see that's what I'm going to do on all these examples. So one period was pi over 2. So 1, 2, 3, 4 spaces is pi over 2. That means each space is 1/4 of that, or pi over 8. That helps me get my scale. So that's one thing I like to do with my graphs, is choose a convenient scale on the x-axis. And then the other thing I like to do is I like to think about what the graph is going to look like before any shifts, either a phase shift or a vertical shift, and then I apply those. So here's what I mean with that. Just thinking of the amplitude as 1, that means I'm going to go up 1 unit and down 1 unit. And then I already took care of my period by putting the appropriate scale. This is a cosine, so I'm going to think of the cup. So I start up at 1, go down and up, and that would make 1 cup. So that's what those pink dots are. Then I apply the shifts. Now again, there's no phase shift. I just have to go down 2 units. So I took each one of these pink points and went down 2 units. That gave me 1 period of my graph. And then I could just repeat that as much space as I have on my graph. And there's my graph. So that's how we graph them. We're going to do that same strategy for all of them. So let's try another one. So why don't you guys try doing this example at the bottom there. I would recommend pausing the graph or pausing the video, but then see if you guys can graph that one. And we'll check in together. All right, let's see how we did first with just our values for A, B, C, and D. Hopefully you guys got these values here. So A is -3. B is a coefficient of x, which is 2. C, it says plus pi. It's kind of like our minus h plus k that we add. We're going to change the sign. So it says plus pi. That means C is -pi. And then D is +2. And then because of that, here's our values here. We have an amplitude of 3. Remember, it's always the absolute value of a. We have a period of 2 pi over b, which is 2 pi over 2, which is pi. Our phase shift is c over b, which is negative pi over 2. And because it's negative, we're going to go left. And then we have a vertical shift of 2, which is up 2. Now, there's something special about this graph, or this equation, whichever way you want to think about it. I have all the stuff listed here, but there's actually one more piece of information that's important from these values that I haven't taken into account. Can you think about what that is? Because these values tell me all of this, but there's one more thing that these values will tell me that I don't have over here. If you haven't figured it out yet, it has to do with the value of a. We know the absolute value of a is 3, so that tells us the amplitude. What about the negative? Does the negative tell us anything? And it does. We're going to have a reflection in this one. If a is negative, we're going to have a reflection about the x-axis. So this should be your graph. Let's see how we did this one now. So here's how I thought about this one. Again, I like to think about my graphs before any shifts, and then I apply the shifts. So I do need to think about the amplitude, the period, and in this case, the reflection. Now, as far as the period goes, again, just choose a convenient scale on your x-axis, and that takes care of it. Since the period is pi, I want 1, 2, 3, 4 spaces to equal pi. That means each space is pi over 4. And then I also want the scale on my y-axis. I'll just keep that as a 1 because I don't have any crazy amplitude. Now this is a sine graph. Remember, a sine graph, one period starting at the origin looks like that. However, in this case, I do have a reflection in the x-axis. So rather than going this way, it's going to go down and then up. So when I'm plotting those initial points, I'm going to start at the origin, go down, and then back up. And I'm going to go down 3 units. So from the origin, I go down 3 units, then back up 3 units, and then back down. And there is my S reflected in the x-axis. So this would be one period before any shifts. But now let's find the shifts. So as far as the shifts go, I have to go left pi over 2 units. Now if 1 square is pi over 4, it's going to take 2 squares to be pi over 2. So I'm going to go left 2 squares and then up 2 squares. So each one of these pink points went left 2 squares to go left pi over 2, and then up 2 squares to go up 2 units. This pink point, left 2, up 2. This pink point, left 2, up 2. This pink point, left 2, up 2. And this pink point, left 2, up 2. And that's where I got these points. But once I have one period, I can just keep that pattern up, and that gets me the rest of my graph. So there we go. There's another one. Okay, here's another one for you to try. Give that one a try. It's at the bottom of the screen there. Try that one out, and we'll take a look together. All right, so here's what you should have gotten on this one. Again, looking at our values here, we can see that A is 3, so the amplitude is 3. B is pi over 4, so the period is 2 pi over pi over 4. Dividing by a fraction is multiplying by the reciprocal, so we actually have a period of 8. C is 0, so there is no phase shift, and we're going to go up 1 unit. So again, as far as my scale on my x-axis, since my period is 8, I want 1, 2, 3, 4 squares to equal one period of 8. That means each square is 2. And I also counted by ones on the y-axis. There's no reflection here, so before any shifts, if I start at 0, I'm going to go up 3 units, down 3 units, and back to the middle. That gets me my S for sine. But then I just have to shift everything up 1 unit. So each one of these pink points went up 1 unit. And then I just continued the pattern, and that gave me the rest of the graph. So there's graphing for you. And now I just have 2 more examples. We're going to go backwards. What if I gave you the graph? Could you go backwards and find the equation? And we're going to do exactly what we did before, just backwards. Now if I gave you the equation, you found A, B, C, D to find these values and then graphed it. Well, from the graph, we're going to find the amplitude, period, phase shift, and vertical shift to find our values for A, B, C, D to plug back into the equation. So let's take a look. Okay, let's say that we were given this graph. I've already got it all marked up, but sometimes the graph will tell you, the directions will tell you whether to use sine or cosine, and sometimes they don't. If they don't, you get to choose. And there's no rule that says always choose sine or always choose cosine. You just choose whichever one you want. But these directions did tell us to use cosine, so we're going to use cosine. Now, cosine, like once you choose, think about the cup for cosine or the S for sine. In this case, because it's cosine, I want to think about the cup. And starting from the origin, or from x equals 0, I should say, I can see a cup right there. So I'm going to use this cup. You can use any cup you want. I could have used the cup on the left if I wanted to. But the convenient thing about using this cup right here is since it starts at x equals 0, there's no phase shift, which means C is 0. It just makes life easier. But I don't have to do it that way. The second example I'll show you, you can do 2 different problems and still get the same graph. So you'll see that in a second. But for now, I'm just going to use this cup. Again, it's convenient because it starts at x equals 0, so it makes life a lot easier because there's no phase shift. But I don't have to. I can see that from the middle, I'm going up 2 units or down 2 units, so that means my amplitude is 2. And because this cup is holding water, there's no reflection, so A is positive 2. I can also see that it completed 1 period in 4 units, so my period is 4. But remember, the period is also 2 pi over b. So if 2 pi over b is equal to 4, I can solve this for b and find that b is pi over 2. So just make this equation to find your value for b. We already talked about, since there's no phase shift, that c is going to be 0. And there's also no vertical shift on this one, so we know d is 0. So that's it. Now you put it together. A is 2, b is pi over 2, c is 0, so there's your graph, there's your equation. Now, I did say, like I said, I could have used this cup over here to the left, and I would have gotten a different equation, but it would still give me the same graph. And like I said, I'll show you on the second example. So let's take a look at this last example, and then we'll be done. Okay, so let's look at this guy. Now, again, I want to write it in this form. The problem is telling me I need to use a cosine. So I want to look for a cup. Now, unfortunately, I can't start at x equals 0 and get a cup. I can only get a partial cup. So the question is, do I start here? Or do I start maybe over there at whatever this value is? Or you're going to see on this one, what if I took an upside down cup? But we'll come back to that. Again, it doesn't matter. Just make sure you choose a full cup. And so if I take a look at this one, so assuming this cup, the amplitude is from the middle. It's going up 3 units and down 3 units. And my cup is holding water, so there's no reflection. A is positive 3. Okay, what about 1 period? Well, I have to look at where the cup starts and where the cup ends. It's going from 3 pi to 11 pi to complete 1 cup. So what's the distance between 3 pi and 11 pi? Well, subtract them and you get 8 pi. That's your period. That's how long it took to complete one period, or in this case, one cup. So again, 2 pi over b is 8 pi. That means b is 1/4. That tells me my b. Now I do have a phase shift, because this cup doesn't start at x equals 0. It's to the right 3 pi units, so my phase shift is 3 pi. Now remember, your phase shift is always c over b. We know b is 1/4, so this gives us an equation to solve for c. That means c is going to be 3 pi over 4. And then the last thing, we can see that this middle line got shifted down 1 unit. That means d is -1. Put it all together. There's A, B, C, D. There's my equation. So that's one way, or another possible answer is down here. What if instead of looking at this cup, I looked at the one I have highlighted here? Now this time the cup is upside down, so I do have a reflection, but my amplitude is still 3. I'm still from the middle, I'm still going up or down 3 units. But because of that reflection, A is -3. Now looking at my period, this time it starts at -pi and it ends at 7 pi. So the distance is 8 pi. So one period that's actually the same thing we got above, which makes sense. It doesn't matter where you start, the period should be the same. It's still going to take 8 pi units to complete one cycle. So again, 2 pi over b is always the period. Solve for b, you get 1/4. The phase shift. If I start looking here instead, I've shifted to the left pi units. So my phase shift is -pi. And if c over b is -pi, I know b is 1/4. I can solve for c and get -1/4 pi. And my vertical shift is still down 1 unit. So now I get this equation. So the last thing I want to do is show you that whether you have this equation that we got in the second solution or this equation that we get in the first one, it doesn't matter. It's the same graph. So to do that, I'm going to take you over to Desmos, and we'll take a look there. Okay, so here we are at Desmos. You can see on the left-hand side, I put the 2 equations that we found. The first equation is from the first solution, and the second equation is from the second solution. There are 2 different equations. Here's the graph of the first one. You can see it in red. Here's the graph of the second one. You can see it in blue. They're the same graph. Blue, red, blue, red. So that's why it doesn't matter which way you look at it. Sure, you'll get 2 different equations, but the 2 equations still describe the same graph. And there's going to be a multiple number of solutions then, an infinite number of solutions that you could pick for this. So anyway, that is the end of the notes here. That's your overview of sine and cosine graphs. Have fun with the homework, and I'll see you in class. Bye.